Hello everybody and welcome to the module on hyperparameter optimization. My name is Lars Kotov, and in this video we're going to talk about the big picture of hyperparameters, why they are important, what they are, and what you might want to do with them in practice. So, as you know, training a machine learning model learns something, namely it fits the parameters of that model to the data that you give it as training data. This could be, for example, the coefficients in a polynomial as a very straightforward example, or as something that's maybe not as obvious. You can also fit the parameters of a tree learning algorithm to particular data by learning the structure of a tree. So by deciding where you want to make decisions and what decisions should be made at the various nodes, and then how you partition the data according to that. The hyperparameters of a learning algorithm now specify what parameters should be learned and how this learning should be done. There are many examples of this. So I've mentioned the coefficients of a polynomial, which are parameters that we might want to learn. Well, how many coefficients are there? What degree polynomial are we learning? That would be an example of a hyperparameter. Others include the number of trees in a random forest, the learning rate in a neural network, or the kernel in a Gaussian process. So these are really very ubiquitous, and these occur with all the different learning algorithms that we might want to apply to a particular set of data to then learn a model from these. Here's a motivating example to maybe make this a little bit less abstract. I have taken XGBoost and I have run this on the OpenML dataset 11, which is the balanced scale dataset. As you know, XGBoost usually performs pretty well, so you might wonder, well, why do I need to worry about this hyperparameter thing at all? Can I not just take a learner and run it, and then I get a reasonably good performing model? Well, in many cases that will be the case, but here, as you can see, with the default hyperparameters for XGBoost, I get an accuracy of about 76% with a standard deviation of about 8%. And if I swap out the booster from the default GB tree to GB linear, then I get an accuracy of a little bit more than 85%, about 85.5%, with a standard deviation of 5.6%. So this is about 10% accuracy improvement, and in particular this is something that falls outside of the range of the standard deviation, as in it is unlikely that this is simply caused by noise, with a very simple hyperparameter change. So all I've done here is swap out one of these hyperparameter values, and of course XGBoost has many more, but even with a simple change like that, we can already, in at least some cases, as in this example here, achieve some performance improvements. So this is really something that you want to have a look at in practice, because it's a very simple change to make, in particular once you have put everything else in place. So you have your entire machine learning pipeline, and you have put everything else together, you have thought about data pre-processing, etc., because in the end you want a well-performing model. You want something that gives you good predictive accuracy, or whatever it is that you're looking for. And if you can improve this with a relatively simple change like this here, then hey, that's fantastic. In particular, we're going to have a look at how you can do this automatically, so that you don't really have to worry about this. You just have to keep in the back of your head that, hey, there's this thing called hyperparameter optimization, and I should try it on my particular data set for the models that I'm considering, because it might give me a performance improvement at very little cost. Okay, so before we can talk about hyperparameter optimization, we need to talk about what hyperparameters are. Hyperparameters have to be set in every machine learning application. This might be obvious or this might be non-obvious, but they have to be set in every application. And they systematically and semantically affect what is learned and how. I've earlier given you the example of the polynomial regression, where when I set the degree of the polynomial that is being learned, I set a hyperparameter, and obviously this has a major impact on both what is being learned and whether I will be able to get good performance. If I try to approximate something that was drawn from a quadratic function with a linear function, I'm not going to get good results. So that's why in this case I would have to set the hyperparameter, the degree of the polynomial, to 2 to get a good model and then good predictive accuracy, just as a very simple example. Now, hyperparameters are not merely the options of an implementation, because you might have seen this before. So all the parameters that you can set when you, for example, instantiate the Python function to do your training, It is a little bit different from that because you can often change a lot of other things in your implementations that you might want to change for various reasons, but that are not really hyperparameters and that in particular don't really affect the performance and should not be tuned as other hyperparameters that we're talking about here. Examples of this include the random seed. This will affect performance, but it's not something that systematically affects performance. There are no expectations that a particular random seed will be better than another across a wide range of data sets, which is what we're looking for here. Other things, debug output level. Useful when something is not working, but it's not going to affect model performance, hopefully. Number of jobs to run in parallel. Also something that will affect things in practice, and you do want to set this carefully, but it's not something that you necessarily want to tune and optimize automatically. We call a complete set of values for each hyperparameter a configuration, and this is what determines how a particular learner will operate and how it will go about learning its model once you give it the training data. Without the configuration, we cannot train machine learning models. And this might be somewhat counterintuitive because you can use a lot of functions in code without explicitly setting hyperparameters. Well, this is because for all of these hyperparameters, there are usually defaults. Usually these are sensible defaults, as in something that will give you reasonably good performance. So we do not need to explicitly set these necessarily. We can instead rely on the values that were set by the person that implemented it, and these are, as I said, usually often well specified, so that in many cases we don't have to worry about it too much, but the values still need to be set. Whether they're set by you or by somebody else doesn't really matter in this context. They still need to be set, so hyperparameters are everywhere, even if you don't necessarily see them. Right, so we want to optimize these values because, as you have seen in the introductory motivating example, this can often give us better performance in practice. Usually the default configurations give us reasonable performance, not in every case, so you do have to be a little bit careful there as well, but usually this would not be the best performance because we cannot have a default that works best in every single case. So hyperparameter optimization is the search through the space of possible configurations, so through the space of possible values for all of my different hyperparameters for the best performing one. Hopefully this is systematic so that we can do a good search and we can get a good result, and we will see a couple of examples of how to do this later on. This can yield substantial performance improvements, and it usually does make a difference in practice. Just as a reminder, here's the formulation of the hyperparameter optimization problem that you have seen in very similar form before already. So we essentially want to find a hyperparameter setting, a hyperparameter configuration, lambda star, that minimizes the generalization error of a model that is induced on a particular training data set and then evaluated on a valuation set. So we have the usual distinction, the usual separation into training and test and validation sets, because we don't want to overfit to our training set. And as you have seen in the previous module, this is a little bit trickier in the hyperparameter optimization case, so you do have to be a little bit careful there. But in principle, we're again interested in something that generalizes. So to summarize, hyperparameters control what model parameters the machine learning training process fits and how. Default hyperparameter configurations often perform well in practice, but usually they wouldn't give you the best performance. Instead, you should optimize a configuration for the given task as the performance of different configurations varies across tasks.